Entonces, en la ciudad hay ciertos sitios simpáticos que algunos de ustedes conocen. Entonces, la catedral, que tiene, digamos, dos tipos de estilos, un estilo románico y un estilo gótico, porque ha sido construida sobre 3 siglos. Hay la abadía de Lepao, que es justo abajo, y que tiene más el estilo intermedio. Y después de eso hay el muro romano, que ha sido descubierto en los años 50 y después se ha, digamos, limpiado un poco porque había mucha basura. Y entonces es muy agradable de caminar cerca de este muro porque después hay el río Sarthe. Podemos pasar también al deporte. No creo que voy a hablar mucho de fútbol porque no es mi deporte favorito y además me parece que el equipo está bajando. Sí. Y bueno, el más importante viene, digamos, de los 24 horas de Le Mans, que es una competición de coche que se tiene cada año, el segundo fin de semana de junio, y supongo que han oído de eso, que no es como la Fórmula 1, es, digamos, de mantener carros durante 24 horas. Evidentemente hay varios choferes. Y lo que pasó, por ejemplo, hace 2 años, creo, es el equipo de Toyota, 1 kilómetro antes de las 4 horas, el motor se ha roto. Y entonces toda la gente de Toyota estaba llorando porque han perdido muy cerca del fin. Evidentemente hay también competiciones de motos. ¿Dónde es esto? ¿Funciona? Ok. De moto y también para los que están interesados de patines. Aquí. Y pueden ver que hay mucha gente. Generalmente es un encuentro internacional. Lo que es agradable es que es más tranquilo que con los autos al nivel del sonido. Porque hay que imaginar 50 autos, por ejemplo, al principio. Y si están interesados para hacer, me parece que es mejor de tener una cierta costumbre de hacer patín. Porque hay el circuito que hace más o menos 7 kilómetros y hay toda una subida al principio. Entonces son más o menos entre 900 y 1000 equipos hasta 10 personas. Y el primero tiene que hacer 3 vueltas y después hay ¿cómo se dice? Un tipo de, ¿cómo se dice en castellano? Un batón que se da al siguiente. Testigo. Ok. Pasaje del testigo. Y lo que hay que saber es que cuando hacen hasta el fin con equipos de 10, pueden hacer hasta 900 kilómetros. Hay que imaginar. Hay algunos, se podría calificar quizá de loco, hacen con un equipo de 2 o 1. De 2, los mejores pueden hacer 550 kilómetros. Y en solo más de 400 kilómetros, entonces durante un día. Entonces hay que estar bien con cierta forma. ¿Qué? Exactamente. Y también hay especialidades, digamos, gastronómicas y hay vino blanco que está al sur de la ciudad. Entonces, no he dicho antes, pero se ubica Le Mans a más o menos 1 hora con TGV, el tren a gran velocidad, cuando no hay huelga, cuando no hay retraso, pero debe ser menos de 1 hora la distancia con París. Bueno, así funciona. Entonces, es la dificultad ahorita no de hacer eso, pero no sé exactamente lo que conocen, digamos, a propósito del Mosbawal. No sé si conocen nada, un poco, mucho. ¿Sí? Bueno, entonces voy a intentar de presentar rápidamente, porque quizá lo que es más interesante es de saber por qué usar la técnica. Y vamos a cruzar con Quique y Gustavo a ciertos momentos. Ellos van a dar más informaciones respecto, digamos, a la instrumentación y cómo ajustar un espectro. Porque al fin la llave de un resultado no es de tener el espectro, porque se hace más o menos solo, pero de ajustar un espectro requiere tiempo y hay que pensar. Porque se puede ajustar fácilmente con un código, pero después hay que dar, digamos, un sentido físico al resultado. Lo que no es únicamente para el Mosbawal, es para todos los resultados experimentales. Bueno, entonces, lo que voy a presentar son los fundamentales, los parámetros hiperfinos, aspectos instrumentales rápidamente. Quizá voy a detallar un poco más la parte bajo campo, porque supongo que no van a hacer. Y aspectos de ajuste voy a ponerme de una manera general. Y como he dicho, Quique y Gustavo van a dar detalles. Hablar un poco de mimos, ¿van a hacer? ¿No? Ok. Y voy a intentar de dar algunos ejemplos. Entonces, bueno, si la técnica se llama Mosbawal, digamos, es debido al hecho que hubo un estudiante de tesis, entonces toda la vida está abierta, que durante su tesis en Heidelberg ha trabajado y al fin de su tesis ha obtenido, quiero decir, el premio Nobel. No después de la tesis. Lo que hay que saber es que tenía el premio Nobel, pero no tenía una posición a la universidad. Lo que es un chiste porque en Alemania es muy estricto. Entonces, hay que empezar para realmente entender con la experiencia de Wood, que ha sido hecha en el 1904. Y entonces, ¿qué consiste esta experiencia? Si no lo han hecho, es de tener un balón que va a contener sodio. Entonces, cuando se va a calentar, se va a evaporar. Vamos a tener un color amarillo. Pero si además vamos a usar, por ejemplo, una radiación del sodio, vamos a ver que hay más luz, que el color es distinto, que es más amarillo. No sé si se puede entender, amarillo y más amarillo. Entonces, ¿eso qué quiere decir? Quiere decir que hay que considerar finalmente los electrones y especialmente el comportamiento, describiéndolos en términos, digamos, de niveles electrónicos. Entonces, el aspecto importante es de saber que cuando hay un sistema que va a emitir, va a salir un fotón, y hay un sistema que va a recibir, entonces vamos a tener primero una desexcitación y después una excitación de un nivel en otro. Y la diferencia de energía corresponde a H nu. Lo que pasa es que en el caso del sodio estamos con niveles electrónicos y el punto importante es eso, es que la energía es el orden del electronvoltio. ¿Ok? Entonces la pregunta que se hizo o que alguien hizo a Mosbawal, el mismo, si se puede hacer algo, pero no jugando con electrones, pero jugando con núcleos. Entonces, el único cambio, porque es casi la misma cosa, excepto que aquí he cambiado nuclear, había electrón, pero aquí el mayor cambio es que no tenemos energías del orden del electronvoltio, pero ahora tenemos energías del orden del kilo electronvoltio. Entonces hay que saber si el proceso puede ser aplicado. Entonces, lo que había hecho Mosbawal no era de trabajar con el hierro 57, pero de trabajar con el iridio 1,91. Y entonces había visto algo, porque a la época no podía entender fácilmente todo, había visto algo, que había un tipo de absorción, y que pasa en una línea, y que dicho efecto estaba, digamos, creciendo cuando bajaba la temperatura. Aunque al principio no se podía entender eso, porque si se considera un átomo libre, entonces vamos quizá a tener, cuando vamos a mandar al fotón, un efecto de retroceso. Y si hay un efecto de retroceso, es como no es la buena época para hablar de eso, con el conflicto, pero si usan, como se dice, una escopeta, entonces vamos a tener un retroceso. No hay que intentar hacer experimento. Entonces hay que tener una idea, ¿qué tal la energía de retroceso? Y cuando se va a emitir, vamos a tener, digamos, el efecto de minimizar la energía, digamos, de hacer un shift hacia negativo, aunque cuando vamos a tener la absorción va a ser en el contrario. Es decir, que al fin tenemos una diferencia de 2 veces la energía de retroceso. Y que la línea aquí de emisión y que la línea aquí de absorción no se solapen. Entonces, no hay resonancia. Y él había encontrado resonancia. Entonces, hay que tomar en cuenta que quizá hay el efecto de temperatura. Pero con el efecto de temperatura tampoco no es igual. No se puede entender. Porque al fin no vamos a tener un efecto, efectivamente, cuando la temperatura baja, este efecto, dicho Doppler, va, digamos, a disminuir. Entonces, el solapamiento, el mismo, va también a disminuir. Entonces, el efecto de temperatura no permite de entender, digamos, lo que estaba observando Mossbauer mismo. Entonces, lo que hay que pensar es que, finalmente, al contrario de las varias técnicas, por ejemplo, infrarrojo, ultravioleta, que se puede usar con gases, que se puede usar con líquido y también con sólido. Y si se pone que el átomo, que ha sido la hipótesis aquí, está libre, no funciona. Pero si se considera que el núcleo pertenece a una matriz sólida, entonces, obviamente, el átomo no está libre. Y cuando vamos a tener el efecto de retroceso, no es el átomo mismo que va a retroceder, pero va a ser toda la matriz en la cual el núcleo está, digamos, atachado, ligado. Gracias. Entonces, efectivamente, diría yo, sin ecuaciones, al lugar de tomar, porque cuando vamos a considerar el efecto de retroceso, la energía de retroceso, vamos a tener a un momento la masa. Si se considera no la masa de un átomo, pero la masa de todo el sólido, vamos a disminuir dramáticamente la energía de retroceso. Y consecuencia, vamos a tener al fin un solapamiento de los picos de emisión y de los picos de absorción. Y vamos a tener dicho efecto. ¿Está claro eso? Ok, gracias. Entonces, se habla a veces de resonancia nuclear, resonancia gamma, o también proceso a cero fonón, lo que vamos a ver después. Pero generalmente se habla de efecto Mossbauer. Entonces, las llaves del efecto Mossbauer es de tener, al fin, un sólido. Es decir, que directamente no se puede aplicar dicho fenómeno a gases, tampoco a líquidos. Ahora, si tenemos un líquido, hay que congelarlo. Y cuando se va a congelar, vamos a obtener una solución congelada, un sólido. Y entonces se va a poder aplicar. Pero si ven en una referencia que la gente ha aplicado, digamos, la espectrometría sobre un líquido, no se puede. ¿Está claro este punto? Y cuando se habla de nanopartículas, vamos a ver después, pero yo lo digo ahorita, una nanopartícula puede ser muy, muy chiquitita. Y a veces vamos a tener un conjunto de una centena de átomos. Entonces, el proceso quizá va a ser modificado. Y se puede anotar que la absorción va a disminuir porque al fin el efecto va a ser menor debido a al tamaño pequeño del objeto que queremos estudiar. Entonces, una solución va a ser de insertar, ¿se dice? Insertar dichas partículas, nanopartículas, en una matriz. Entonces, para favorecer la rigidez del sistema. Al contrario, lo que pasa es que vamos a establecer interacciones químicas, electrónicas, con la matriz. Entonces, hay que pensar cuando se va a interpretar los datos que no tenemos una nanopartícula libre, pero está, digamos, correlada, está totalmente insertada en una matriz. Y puede ser que haya modificaciones al nivel de la superficie y de las interacciones. Entonces, eso hay que pensar. Bueno, entonces, ¿qué pasa? Ok. Bueno, lo que estaba diciendo es el problema, digamos, de la absorción, emisión, y totalmente centrado con el fenómeno, digamos, de sistema sólido que no tenemos átomos libres. Y por esa cosa, Mossbauer ha obtenido el premio Nobel en el 61. Creo que es la segunda persona, la más joven, que lo tiene. Hay otro que más joven que lo ha obtenido con, ¿cómo se llama? No me acuerdo. ¿Qué? No, es otro. Bueno, no importa. Bueno, entonces, ahora hay que mirar las ideas y igualmente, voy a repetir para que sea bien claro para vosotros, que es este efecto, digamos, de transferencia de energía de retroceso, e impulso al nivel de la red. Y entonces, lo que pasa es que tampoco cuando vamos a mandar energía al sistema, es como si de una cierta manera vamos a calentarlo y entonces vamos a excitar al nivel de la red. Y entonces podemos crear algunos fonones. Supongo que saben que son fonones, ligados a, digamos, a las vibraciones atómicas. Y entonces, si la energía es fuerte, vamos a crear fonones. Eso es afuera del efecto. Entonces, no se debe crear fonones. La consecuencia, a veces se puede llamar el efecto como el proceso a cero fonón. ¿Ok? Entonces, a cada vez estoy adelante. Ok, no tengo más que decir. Entonces, una cosa que hay que hacer es caracterizar la línea. Vamos a tener líneas, ¿y qué tal la forma de la línea? Entonces, no se hizo temprano eso, porque se hizo experimentos antes, se hizo teoría antes, pero al menos después del 25, después del conocimiento de la mecánica cuántica. Entonces, se puede, digamos, describir la línea Mossbauer a partir de la absorción efectiva, ¿ok? Y tiene un perfil lorentziano. Bueno, no voy a discutir todos los detalles. Y hay un montón de parámetros, pero me parece que el punto importante es de saber que tenemos una línea con perfil lorentziano. Ahora, después, eso es, digamos, la idea en situaciones muy perfectas. Porque vamos a ver después que la línea puede ser distorsionada. ¿Por qué? Porque, digamos, los núcleos, o mejor dicho, los átomos, dentro de la matriz, van a tener también distorsiones. Y si tienen distorsiones, vamos a modificar el perfil lorentziano. Pero mejor es de describir, digamos, un espectro a partir de una suma de picos lorentzianos, de formas lorentzianas. Puede ser a veces, vamos quizá a ver sobre un ejemplo, que tengamos un perfil gaussiano de lorentzianas. Por ejemplo, en sistemas amorfos ideales. Bueno, si estamos de nuevo con el caso del hierro 57, podemos ver que hay una energía, digamos, bien precisa. Supongo que Quique y Gustavo van a discutir a propósito de la fuente. Entonces hay un tiempo, disculpa, hay dos, lo que es importante es de acordarse que estamos con el fundamental, que está, ¿cómo decir? Un estatuto, ¿no? Hola. Sí, pero el estado, un medio, y un estado, tres medios. Estado, ok, estado. Hay también aquí el ancho de línea de la fuente, y la fuente tiene que proponer algo monocromático, es decir, que fuera una sola línea y su width, su ancho está aquí. Entonces pueden ver que ya, es muy baja. Exactamente aquí es el medio ancho, a media altura, porque el ancho total va a ser de 0,19. Ok, entonces es decir que si encuentran, por ejemplo, un sistema con un ancho de 0,15, va a ser menor que el inicial. Entonces no puede ser. Bueno, y después hay este parámetro. Ahora, el más importante es de mirar, digamos, el ratio entre este ancho y el E0, característico de la transición. Y podemos ver que es algo que es extremadamente bajo, 10 a la menos 13. Y entonces eso es la clave para poder tener acceso a las interacciones hiperfinas. ¿Ok? Bueno, entonces tenemos que hablar un poco del F-factor. Alors, como he dicho, hay que tomar cuenta durante el proceso de absorción qué tal el estado, digamos, de la matriz. Si está completamente fijo, supongamos a 0 Kelvin, todo está fijo. Va a ser, digamos, ideal. Pero cuando estamos, por ejemplo, a temperatura ambiente, a veces se puede hacer medidas a temperatura altas, hasta 1000 grados, va a depender, digamos, de los sistemas. Entonces, ¿qué pasa? Porque hay un tipo de competición con los fonones. Y como he dicho, no hay que tener un fonón. Y hay que caracterizar finalmente la eficiencia del sistema. Si todos los núcleos van a participar o si solamente una parte de los núcleos van a participar. Y entonces eso se ve que hay un factor que se llama el factor F, que corresponde a lo que se puede llamar la fracción sin retroceso o el factor Lambda-Bauer, que va, digamos, a caracterizar el acoplamiento entre el núcleo que va, digamos, a resonar y su entorno. Y eso se puede describir con formas matemáticas bajo esta manera. Un ejemplo, por ejemplo, ya. Si supongamos un polímero, y un polímero tiene una rigidez muy baja. Polímero con átomos de hierro. Podemos hacer una medida a temperatura ambiente, nada. Si bajamos la temperatura, a un momento vamos a aparecer en un espectro rápidamente. Al fin, ¿qué pasó? Es que hemos pasado la transición vitriosa. Es una manera indirecta de la medir. Pero es una demostración que cuando, digamos, hay una cierta rigidez de la red, vamos a poder tener una señal. Igualmente, y es también una pregunta cuando se trabaja con los nanoestructuras, si tenemos un átomo que está al centro, está ligado con su entorno. Si estamos con un átomo a la superficie, ha perdido vecinos. Entonces está más tranquilo. Y cuando va a recibir el fotón, ¿qué va a hacer? Y eso es muy importante. Entonces no vamos a detectar, digamos, de la misma manera un átomo que está bien ligado con su entorno, al contrario, digamos, de un átomo que está sea una matriz polimérica o, por ejemplo, a la superficie de un sistema. Entonces, eso es muy importante. Ahora, típicamente tenemos algunos valores para el hielo, que estamos a casi 0,9 a 4K. Sin embargo, estamos a 0,7 a 300K. Ahora, la pregunta ahora es que si tenemos una muestra que va a contener distintos tipos de hielo, si todos están asociados al mismo valor de F, a la misma eficiencia, digamos, de resonancia. Es una de las primeras preguntas. ¿Sí? 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 Dos sitios cristalográficos. ¿Sí? Claro, claro. Sí. Depende de cada sitio, de cada entorno. Alors, lo que es lo que mostrado César durante su presentación, y entonces una solución es de hacer medidas frente a la temperatura en las mismas condiciones geométricas, porque si una vez tú haces con esta distancia y la otra vez con esta distancia, no se puede comparar. Y entonces, bajando la temperatura, tú vas a poder tener acceso a la superficie de cada componente asociada a tus dos tipos de hielo. Y tú vas a comparar. A veces están muy paralelos, pero a veces no están paralelos. Y eso es muy importante. Y lo que ha mostrado César, digamos, en las feritas. Y efectivamente hay una diferencia. Alors, estaba pensando a otra cosa ahorita. Caramba. Bueno, no importa. Ah, sí, sí. Sí, sí, tienes razón, sí. Sí, sí. Pero como no conocemos todo sobre la superficie, va a ser difícil, digamos, de poder discriminar directamente efecto de corazón y efecto de superficie, y entonces el factor F. Se podría. Hay que ir con velocidades mucho más grandes. Sí. Sí, sí, y lo que quería decir es que, por ejemplo, en este caso tenemos una diferencia no muy importante y generalmente cuando llegamos a 77, después hay casi un plato. Por ejemplo, el valor de 0,7 a 300K, 0,9 a 4K y podría ser 0,87 a 77. Tenemos casi un plato. Es porque en la mayoría de los estudios, cuando se hace la medida a temperatura ambiente, es sin discutir el problema de ajuste, tenemos un primer valor. Pero después es mejor de ir a 77. Y en este caso voy a mostraros un ejemplo más tarde. Y okay.
but okay. Because I did my PhD in infrared.
Okay.
And infrared there is a similar case, of course, because it's what we intended.
Yeah.
Only the operator is the dipole operator,
Of course.
and I open the calculations and use the participation theory, and then you can take the rules, of forbidden the selection rules, bad method. You can take the selection rules from the calculation. I'm just curious, can you open, it's the same process, that is, if I use proper activation theory in this calculation here. Not, I don't want you to do it. I'm just curious. If you take this integral and you use the...
Yeah, yeah, it's possible.
So it depends on the case. The case is very simple. Maybe you have a combination of half many factors, where you have solve the calculation theory. You want to have an analytical expression. There would appear also selection rules.
Yeah, sorry, it's because I was asking about the basic theory, because in infrared you do use perturbation theory, and you prove that if there is no variation in the dipole moment, you will not have infrared absorption. You get the integral, and you prove that there is zero if you...
That applies.
Okay. I was just curious if you can
Maybe you
get
have
to something similar.
several possible transition lines, but you only can observe a few of them.
Yeah. Okay, so I will not repeat all the first part in English, but now I speak in English. So what I wanted to say before, in the case, for example, of tin 119. So, for example, the F factor at room temperature is about 0.4. And it is about 0.8 at 77K and 0.9 at 4K. That means, in some cases, and to reply to the comment of Julian. So we can have at room temperature, for example, 60-40 for two components, for example, in the case of tin 2 and tin 4. But at 77K, you can observe the opposite. So to reply to the question of Julian, so you can easily distinguish, and you can have a strong difference between room temperature and 77K. I think in the case of tin, it's much more important than in the case of iron.
Maybe it's important to say that so far it's a local field. That means if you are in two concentration, so then dynamic and local dynamic can be different. So that means you have different Lie factor, which is a factor
Of course. Mm-hmm.
That's the reason that it is said.
Yeah. Okay. So, conclusion. So the Mossbauer effect is optimal if you have, of course, a small shift of atoms, much lower than the wavelength. If the temperature of the sample is much lower than the debye temperature, so as we were discussing, so this problem of rigidity in terms of debye temperature. Of course, usually the transition energies are less than 150 kilo electron volt. Now, of course, it's difficult to see some effect when you have some atoms with a very low mass. And we will see just after what about the possibilities by scanning all the periodic table. And of course, we need a high debye temperature. So, as I mentioned yet, we have some constraints. It is not possible to observe on gas and liquids. You need some solid state. If you have a liquid, there is a possibility to freeze it down. Okay, and of course, the effect is much more important at low temperature than at high temperature. The reason for which the possibility is to follow versus temperature the F factor, which can be established from the surface of the absorption area, or the surface of absorption areas if there is different components. Okay. So what I have mentioned also, I'm sorry, in the case of nanostructures, so take care of the surface effect. So we are coming, as promised, to this table. So of course, this table has been established by some people who are collecting all data from references containing some Mossbauer studies. So you can see different colors. So the yellow one is for two isotopes, iron and tin, which are highly used. Iron, why? Because you can find iron everywhere. So of course you have in a lab, as there is, for example, in steels, there is in a human being, there is also in soils, there is also on Mars planet, so there is everywhere. Of course, tin is much more reduced, but there is also the interest is because of F factor. Another point also, because sometimes we need money, and we have to buy some sources. And in the case of both iron and tin, we have a lifetime of about 9 months. So what does that mean? That you buy a source which with certain activity, 9 months later, the activity is divided by 2, and so on. Because you have some isotope, the lifetime is about a few seconds. So that means when coming, it is not active. So you need to work with some cyclotron. No, not cyclotron. Cyclotron. Okay. So I presume they will speak about source and so on. Yeah? Commercial and so on. Okay. Okay, no, but I have other thing to comment. So you can see also that you have some rare earth. So as I mentioned, you have cases as iron and tin. You can do some experiments at room temperature. But if you are using, for example, gadolinium or gold, nothing. You need to work at very low temperature with liquid helium. So that means you need some specific infrastructure. Of course, in the case of iron, it's easy. I would say whatever the place in the world to do Mossbauer. Room temperature is enough. You can have a nice spectrum after, let's say, a few hours, one day, it's okay. So another comment also is with europium. So europium, time life is 82 years. So if you buy a source, you have time to do experiments. Nevertheless, because there is strict rules, and unfortunately the rules are everywhere, after 10 years, you have to take back your source. In the case of europium, it's the same. So finally, we are going to take back sources with a large activity. The people who propose this are not scientists. They are only administrative, because they consider that 10 years it's enough, whatever the isotope. Yeah? On sources. But after 10 years, you have not to send back. Ah, okay. Okay. In Argentine? Because in France, it's totally forbidden. After 10 years, we have to get back the source. Okay. So, if you want to do europium, better to come in South America. So now, as I mentioned, so we are the technique, which is of course a local probe technique, because we are looking to the surrounding of some nucleus. I mentioned that we are sensitive to hyperfine interaction. Okay, you have, for example, X-ray diffraction, you are sensitive to the number of electrons. So you will send your X beam, and you will get some information about the electrons which are located in the sample. In this case, we are going to detect only some nuclei in iron. So that means we are much more restricted. If there is nickel, cobalt, we have no idea. Only iron or only tin. It is selective on local technique. So now I will not discuss on equations, but the idea is to present, of course, what about the position of nucleus, and what about the environment in terms of electronic interactions. So you can write this equation, and of course, after, it's necessary to decompose its contribution. And we will see that there is two main contributions. The first one, as it is mentioned upstairs, the monopolar electric interaction. Okay? And of course, as it is mentioned, so you can consider that the nucleus will occupy a spherical volume. But in fact, it depends, because sometimes, because you have a lot of movement of electrons, you can have some intersection across. So that means you are sensitive to, finally, the electronic density combined to the nuclear density. Okay? So that means, of course, you can write a lot of equations. So I don't want to discuss a lot on the equations. But essentially, you can establish that you have a relation giving the isomer shift. The isomer shift is the cousin of the chemical shift in NMR. We are speaking about the same quantity. And you can see here that you have the product of some nuclear energy, density, the last term here, and on the electronic density. Okay? So, to go rather fast, the isomer shift is due, finally, to this quantity. You have to do the difference between what happens in the source and also what happens in the absorber. But in both cases, electronic and nuclear density. So you see that you have to combine all of them. So finally, it is due to a double differential effect. So the reason for which we will not extend on the equations, but maybe it's easier to discuss from the different states. So you have your fundamental state, your excited state. There is a small shift at the source. After, you have your sample, and there is also the two fundamental and excited state. And you will see this effect, but it could be modified. And the isomer shift corresponds to the difference between such energy and such energy. Okay? As I mentioned, we can put a lot of equations, but I think it's not, we have no time and it's not so interesting. So now, when we look on the scope, what happens? It happens that we have to discuss after the problem of zero in energy, but we have a kind of shift of the line. And the shift can be established in terms of energy, and it corresponds to the isomer shift. So the name is isomer shift, of course. So now it's possible to complete the calculations. And one can see that in the case of, iron 57, so we have this quantity, which is very important, which is negative. And it reflects the difference between the energies associated to the excited and fundamental levels. So now, in the case of tin, for example, such a value is positive. And you have to know very well this, because sometimes how to interpret some evolution of isomer shift in a sample, in terms, for example, of pressure. So if there is some extension or decrease of the volume. it will influence on the value of isomer shift. So now, why? We have some parameter, okay, but what to do? And this parameter is very important, especially for the chemist, because the main question of the chemist, they are doing some sample. What about the valency state of iron? Is it metallic iron? Is it iron 2, iron 3? Sometimes, why not iron 4, 5, 6, when you have more exotic systems? Tambien, sorry. Also, there is a situation of you have some electron, they are jumping between iron 2 and iron 3. Problem of electron delocalization. And the isomer shift value will be dependent on the grade of delocalization. Okay? But if we have something which is dynamic, we have also to consider that what about the time measurement of the technique? So it's the same problem when you are taking in photo some car, for example, at the 24 hours of Le Mans. If you are using 1/1000th of second, or if you are using 1/10th of second, the photo will be different since the movement is the same. So we have the same here. We have to take into account the characteristic time of measurement of the Mossbauer technique. And it is dependent, of course, on the isotope. And in the case of iron, it is, let's say, in the range of nanosecond. So that means either your movement is larger or smaller than the nanosecond. So you will have either a system which is blocked or which is moving. So that means this parameter is very important. Another point also is, what about the spin state? Yes, the spin state. Maybe it will be easier to see here, because it's possible to collect a lot of results. And finally, you can see, according to the valency state, iron 1, 2, 3, 4, 5, 6, and iron 0. And you can distinguish, in some cases, if you have, for example, high spin state in the case of iron 2, or low spin state. In some cases, also high spin state, low spin state, or intermediate spin state. Of course, if you are there, no question. But if you are there, much more difficult. But of course, you know what did you introduce in your sample as chemist. So you may have some ideas if you have preferentially iron 2 and iron 3. But in some cases, you don't know. The use of the Mossbauer technique can give you the solution. Okay? And of course, maybe in some cases, you can play with temperature. If you play with temperature, maybe you can see some changes. So all this is very important from this first hyperfine parameter. Is it okay for this? So now, a second one, which is related to the electric field gradient. Alors, the electric field gradient corresponds to the second derivative of the potential. And of course, it can be written as a tensor. And as tensor, it's possible to calculate the eigenstate and so on, to have some diagonalization. And from a mathematical point of view, of course, usually you can write this parameter, which is called eta, which corresponds to Vxx minus Vyy over V theta theta, assuming when your tensor is diagonal, the main axes are like this. You have a kind of rule. In such a case, your asymmetry parameter is between 0 and 1. Okay, in this case, you have V set Z equal to A Q set Z. Okay, so after, as problem of quantum mechanics, what you have to do is to write the Hamiltonian and to establish what about the solution. So you have to solve it, and to calculate, of course. Yeah, so I will skip the details. And what it is important at the end, because all the mathematical details can be found in many textbooks. Okay? So, at the difference of the first hyperfan electric interaction, now you will split your excited level. But note that the fundamental level is not split, because you may have -1/2, +1/2, and so on. So that means you have a partial degeneration. And what happens? You have to apply selection rules, and at the end, you will obtain the possibility to have two transitions. Okay? Two transitions with such, I would say, such states. And finally, between the two sub-level, you will obtain a doublet. So now we have first the isomer shift, which corresponds to the center of gravity. So it is given here, the distance between the center and the zero. And you have the splitting, corresponds to the distance between the two lines, and corresponds also to the distance between the two sublevels. Yeah? Yes, at the nucleus.
The nucleus.
Yeah.
It's quite weird because when we learn in graduation, people, and I am one of the teachers that do this, we usually consider that you work with a partial, let's say, as if near the nucleus there is no interference fluid.
Of course. You assume that the nucleus is pure spherical.
Yeah. Oh, sorry.
You assume that it is pure spherical.
Yeah, you take the first levels and the nucleus, and then you work with the atoms if it was hydrogen, if it has only one electron.
Yeah. Of course. Yeah, you're right. Yeah.
And I will teach this semester, and it's quite interesting to know that, well, there is difference.
Yeah.
Not only the graduation, we did it in the math degree. And you have the split. This splits to the change in the circumference of the.
No. Yeah, it is due to the symmetry of the charges around the iron nucleus, around the iron atom. Okay. Two.
How severe the nucleus actually is, because if it's elongated to each the local charges, it will change the.
No. Yeah, maybe I missed to mention this. Now we are looking to all surrounding charges. The first corresponds to a local problem, the nucleus associated with its own electronic shells. And now we are looking to all charges, how they are distributed around the nucleus probe. No, out of the valence. You have, for example, a network. You have your local probe. On the around, you have plenty of atoms. And you are looking now to this environment. That means, what I wanted to say is that here you have some asymmetry. In the case, for example, the two lines are the same, so there is no degeneracy. That means you have a cubic cell, cubic symmetry. Cubic symmetry means, considering the reference located on the iron atom, if you have one charge located in plus x, plus y, plus theta, you have the same one in minus x, minus y, minus theta. Because sometimes people is confused. We have a cubic shell. We have a cubic symmetry from the crystallographic point of view. But you may have some cubic lattice, but you have some splitting. Okay? Is it okay for everyone? So, and consequently, we have to distinguish different contributions. Because of course, in the case of iron 3 plus, your electronic shell is complete. Okay? And how it will interact. In the case of iron 2, it's a 3d6. So you have one electron which is free. And so, again, you can discuss in terms of equation, and you will see that if you have some sample which contains iron 3, only the shell is complete. If you look versus temperature, it will be the same. Now, if you have a change of the symmetry in terms of crystallography, you might see some changes. And I hope to show you some example which illustrates how the technique is sensitive. Okay? In the case of iron 2, you will see some evolution versus temperature, or better said, low temperature, so the splitting will increase, and you have to apply the crystal field theory. Edson? Ah, yeah?
Probably is. So it's a question from Nishikala. So she probably is asking you about the isomer shift, because she said that I suppose that isomer shift. So iron 3 plus in a half state and 3.5 state are given almost same value at higher end, and 0.2 to 0.50 approximately. How to distinguish between them? And also, I want to know if 56 iron convert to 57 somehow, maybe by neutral irradiation. Is it possible to find out the converted 57 iron? I mean, by Mossbauer spectroscopy. So the second question, maybe I understand. If you put your sample, which has, let's say, 95% of iron 56, and then you irradiate the sample, can you believe that by neutron irradiation you increase the F factor? That's probably her question. That's one point. And the other one, probably, I'm not sure that she's want to talk about isomership, but I could not get the question as well. Rafinha, can you put the question on the screen, please?
To reply to the second.
Porque eu tinha saído.
Probably, so I was out, and you put some isomership schematic. Yeah. So, and she asked probably that iron 2 plus and iron 3 plus, I'm not sure. At the higher end, yeah, that's it. Okay, that's the spin. Yeah. Okay, and
the nature of spin. As I mentioned, you have the valency state. I don't know if he or she is.
She
is listening. But
yes.
You have both the valency state and the nature of the nuclear state.
Yeah.
Okay. So you have, of course, in some cases.
Make a question, Jean-Marc.
Okay.
He's going to increase to put 20. No, 50. That's fine for me.
Yeah. So it's a good question about how to distinguish.
Yeah.
So it's not so easy. For example, there is one case, and I have worked on it, is how to distinguish when you have, for some minerals, you have pyrite in addition to other systems. So other system containing iron 3 plus. But pyrite, Fa(S2), is composed of there is iron 2 plus. but in low spin state. And of course, it's difficult to distinguish. So there is no direct method. So we have looked by comparing our Mossbauer data with some other data in order to not to conclude, but to estimate that the maximum it could be or not. Because of course, the two tablets, are strongly overlapped. To the first question. To the second question, if I understand well, of course, it's possible when you are irradiating using different techniques, but it depends. What about the energies? Because I remember to have worked on systems which were irradiated with neutrons. The objective was to modify the valency state and to modify also the position of iron from octahedral in tetrahedral, or vice versa, in the case of garnet. But the energies were too low. It seems to me that you need strong, very strong energies. But I don't know if I replied to this question, or if someone has some comments.
Please, could you repeat? No, I think from the question that she wants to find out if you can distinguish the converted iron 57 from the original one.
Maybe for some people, with iron 56 is totally mute. So you can wait 2 years, you will not obtain a spectrum. You can obtain a spectrum only with iron 57.
Yeah. So suppose that you have a metallic iron. So she is online. Suppose that you have a metallic iron, 2% of iron 57. So you have the fraction from Mossbauer, okay?
Yeah.
And then if you irradiate this sample with neutral, with some energy which can convert the 56 isotope to 57. So we are going to increase, and if you keep the conditions, so you increase the fraction, and then from the relative change, you may estimate how much percent you have convert from 56 to 57. Probably that's the point.
Yeah.
Okay.
So it's possible to estimate, but it's not possible to identify which ones. Of course, and as you mentioned, it's necessary to work in exactly the same conditions to see an increase of the F factor.
Very probably you may have a lot of energy
Yeah.
into the nuclear reaction, and this nuclei, no, the converted nuclei, maybe they end in an interstitial position, or I don't know, they may appear in a different environment. I am not sure.
Okay. So,
one comment. Only thinking in the question that is very interesting. And if it were the sample made with iron 56, only with 56, and you irradiate it, in that case you will see only the converted one.
yeah.
Okay.
Yeah. But it's difficult maybe to have a pure iron 56 sample. Yeah. So it's possible to switch.
Professor, so I do understand the theory behind, but I'm pretty sure they have already done it. For example, they build a sample with 100%, almost 100% iron, take the Mossbauer spectra, and then they dope a little bit with, I don't know, cobalt. And they keep increasing the doping in the sample. So you can see no difference due to the cobalt doping.
So finally, your question is: you start with some matrix
Yes.
on with iron essentially,
Yeah.
and after you are going with some sample, which the composition of which is iron 100 minus X, cobalt X.
Yes.
So if you consider your matrix, at the beginning, iron is perfectly surrounded by iron.
Yes.
After, if you introduce some cobalt, you will have sometimes in the next neighboring of iron one cobalt atom. That means you will break the symmetry.
Oh, okay.
So of course, if you have one cobalt among 10 power 20, it will not be efficient. So of course, it is dependent on the doping content. And there is a lot of people who is doing this. So the difficult point is to be very close to zero. But of course, and I think I have some examples, so as you are modifying the neighboring, the technique is sensitive. So it's good to your question, because if you are working with X-ray diffraction, because the number of electrons in iron and cobalt is rather similar, X-ray diffraction is not able to detect any change.
Okay.
So that means that why the technique is so sensitive.
Okay, thanks.
Is it okay for everyone? Okay. So I have to go. So to finish for this, so I think I did not maintain all the transparencies to shorten a bit, but please remember such points. And of course, there is also a contribution of conduction electrons, but the contribution is quite low and it is restricted in metallic systems. So now, of course, if we consider magnetic materials, so for those who were attending the conference, I showed such a slide. So it's only to put the main elemental concepts. So what is a magnetic material? So I am speaking, usually it is a kind of salad, where you need some magnetic energy, and the magnetic energy results in some exchange between magnetic moments. And the exchange is either ferro or antiferro. You have some anisotropy, better said anisotropies. So with different forms of anisotropy. And you have also the dipolar contribution. Okay? And finally, you have the Zeeman effect. So from such, so you have some kind of draw in between. So you can establish a lot of kind of keywords, characteristics of magnetic materials. So for example, magnetic moments, magnetic order, phase transition, and so on. Okay? So now when the material is containing iron, of course, so you can again write the Hamiltonian, which will be now the Zeeman Hamiltonian, because you have a magnetic moment which will interact with neighbors and or external magnetic field, if any. So you write all the equations, okay, and at the end, what you will get, you will see you have a complete degeneracy of your nuclear levels. Instead, a partial observed with electric interaction. So for the fundamental one, you have -1/2 and +1/2. And for the other one, you have the distribution. Note that here, it's not an error, because the gyromagnetic factor is negative, opposite to that of the excited level. And now you have to apply the own rules. You remember? Difference, plus or -1 or 0. So that means, by such a way, you can establish that it exists 6 possible transitions. Okay? Sometimes it's possible on some spectra to observe some forbidden transition. So, 6 lines. I will discuss a bit the intensity just after. And you can correlate the intensity, the distance in terms of energy, with the position of lines. Okay, so now what you have the distance between a priori the external peaks, and the distance corresponds to the hyperfine field. Okay, I mentioned a priori because sometimes we will see maybe after that they do not correspond to the external peaks, the more intense peaks. Okay, so now if we made a kind of short view, so you have seen the effect of the, the monopolar electric interaction, the dipolar electric interaction, the Zeeman effect, magnetic interaction. But here, of course, in a sample, you have to mix, because of course physics would not be so interesting if there is no complexity. Okay? So you will mix, and of course, you will see that you have some changes. You will add the contribution here to the Zeeman levels. And you will see a modification of the position of some peaks. But sometimes you have to take the opposite, because the quadrupolar interaction is much more important than the magnetic interaction. So I did not put the scheme here because it's much more complex. Okay, so to make, again, something to shorten. So electric monopolar interaction, you are sensitive to valency state and spin state. Okay, with this one. So after the electric quadrupolar interaction, so you can detect the symmetry of charges, or better said, the asymmetry of charges. But you cannot correlate directly. This splitting is larger than this splitting, so it's much more asymmetric on how. It's difficult. But it is totally related to your question. If you have a lot of cobalt in your iron matrix, you will split into, at the beginning, a singlet. The singlet probably will be broadened, and after you will give rise to some doublet. On one, better said, with sextet, because in such a case you will add sextet, sorry. But in any case, you will disturb the profile of lines of the sextet. Okay, and then the last point. So one point is also interesting, is to analyze the intensities of lines. Because we will see after that it's very important to know them. So the same, you have to apply quantum mechanics using the Clebsch-Gordon coefficients, and you will arrive to such things in the case of quadrupolar doublets. So you have 3 cases. The first one, when you have to consider the orientation of the electric field gradient respect to the main direction of the gamma beam. So you will get either such a situation or such a situation, which can be rather extreme. But usually you are working with some powders. So only to repeat, what is a powder? It's a random distribution of small objects, microcrystallites or nanocrystallites. But in such a case, in some cases, you can see that the powder is not homogeneous. Because when the powder is well random, you have a pure doublet and the intensities are the same. And sometimes you will see some asymmetry. So starts the problem. Where does this asymmetry come from? Sometimes you have some samples. For example, in some clays, I would give another example. If you want to put some coins on a table, it's difficult to have a random distribution of all coins. So you will prefer some direction. What it is called usually for X-ray diffraction, preferential orientation. And you can see a change on some peaks. But in this case, in the case of Mossberg white, will be the same. So that means one solution is to rotate the sample respect to the gamma beam. If you see some changes in the intensities of lines, that means it is due to some preferential orientation. If not, it can be due to other things. Or sometimes it is only due because you have 2 components which are superimposed with very close hyperfine parameter values. So, okay. In the case of sextets, you can see different situation. And what it is important that, back. So, random distribution, powder, you have 3 to 1, 1 to 3. You have to remember that the external lines on inner ones ratio 3:1. But for the intermediate lines, it may change. And of course, here you can see that you have the situation 3:4:1 and 3:0:1. So that means you have 90 degrees between the direction of the magnetic moment on the direction of the gamma beam. On here, it's 0 degree. Conclusion. So, I will give Kike and Gustavo to speak on this. But, so yeah, you will discuss on this?
I hope so. I don't know what you're going to say.
But I want to say that Mossbauer spectrometer is composed of some generator of movement, because you have your source. If your source is fixed, you have a single energy. How to have a scanning of energy? By Doppler effect. You know what is Doppler effect? Okay, so if you have Doppler effect, so that means you will move the source and you will provoke a scanning of energy. So you have your sample, your source, your detector, you have a lot of electronics, and you will get, finally, on the scope, this kind of image. Not so interesting that the last holidays, but okay. And why you have twice? Because the source is moving, go up, go down. Okay? And after, the idea is to superimpose the two parts to get the final Mossbauer spectrum. Okay? So our facilities in Le Mans, so to do some measurement versus temperature with a cryostat, to do versus magnetic field, and here it's a cryofurnace which allows to do low temperature and high temperature in the same box. I will show with one example the interest. So MIMOS, a few words, as it is in the word, MIMOS, miniaturized Mossbauer. So the idea was born in beginning of 90s to go to Mars only and to do some Mossbauer. So they were asking to some PhD students, no one was interested. So the idea first was to create a very small spectrometer. And it was achieved. So look, the dimension of this spectrometer. Then it was sent on the planet. There were some tries in Arizona desert to check how it was working. And finally, there were two expeditions, Spirit and Opportunity. For one, the launch was on June 2003, and the landing was 7 months later. So, of course, not so easy to go to Mars. And the first spectrum has been registered there. Okay? So, of course, there is two main problems. The temperature on Mars is not stable. And the differences are very important. So that means sometimes for one day, one Mars day, it's necessary to divide the time, because for some systems, the hyperfine parameters could be different. So it is exactly the same. If you do some spectrum, you are starting, the temperature is 77 K, you have no more nitrogen liquid, and one day after you arrive at room temperature, so you have superimposed different states established versus different temperatures. So it was necessary to overcome this point. And the second point also was the dust which were on the window. So it was necessary to clean sometimes to prevent to have systematically the same component. But of course it was used on Mars planet, but it was used also possibility on Earth. For example, it's easier to take MIMOS, to take it to go to the cave than to take the cave to the lab. Okay? And also for some application there. Another application is, for example, to detect, to check what about the state of some metallic system for nuclear power plants. Because of radioactivity, it's better to send the robot with MIMOS than to send someone. Okay, so now the second point, the sampling. On sampling appears to be a very easy problem, but it's not an easy problem. Of course, when you know, for example, you are working with a chemist, I have done this, you can estimate very easily the quantity of sample to put in your sample order. But when you are working with, for example, rocks, it's quite difficult. When you are working here, it's also quite difficult because you are looking to identify the different phases. So I remember I have done something similar to this with some colleague from geology. And when I asked him, I need 5 milligrams of iron per square centimeter. So large eyes, but I am working on several tons. Okay. So the idea, because it was to study the different layers, the idea for him, please, you prepare 10 samples for this point, for this point, for this point, and so on. And finally, I got 50 or 60 samples. I have checked for 1 point that the spectra were systematically similar. It was. That means it was working very well. And after, it was possible to compare the different zones. But the main problem was to have small quantity also, but not too large. Why? We will see after. So, of course, in the case of some studies of this, it's difficult to know what about the quantity of iron. It's difficult to dope with iron 57. You can ask to the person to take, but I don't know if it will be okay for this person. So that means usually you need a large quantity. And the spectra are not so easy to get, so the statistics remains quite low. The same for leaves, because you have iron leaves on roots, so you can apply. As I mentioned before, so you have some liquid, you cool down. Okay, and so you have to remember the quantity is quite small, 5 milligrams of iron per square centimeter, providing it's easy to establish a quantity. If you put much more, you will change the profile of spectra. Okay, so I think there is some here. So look, 2 spectra on the same sample, on the left side, but not the same quantity. And of course, after you can imagine a lot of models, very sophisticated, and finally, when you look, because one is due to thickness effect. Of course, it's possible to make some corrections, but better is to start, if you have some possibility, to start with the ideal quantity to prevent sophisticated complication. And as I mentioned before, there is some problems sometimes with small nanoparticles. So the limit is there. If you have some samples, you have a chemist, I am not able to prepare a large quantity. Okay. But do you know what about the content of iron? Yes. So you calculate the surface should be 2 square millimeters. Very small. Because typically, I don't know how is it in your labs, but we have something with 1 centimeter radius. So what you can do is to put a screen of lead to prevent to have a very low effect. If you concentrate according to the surface which is ideal, you can get a nice spectrum. And once I had a few milligrams of powder, I made some hole with some peak, very small one, maybe the diameter was less than 1 square millimeter, and I was successful in 1 day to have a good spectrum. So that means it's very important, because if you put your sample like this, you may have 1 month to have bad statistics because the background will be very high. So it's very important. And it's better to spend time to prepare the sample before, to optimize it, and after you will have time. On the contrary, you will lose time. Okay? So the problem, one quadrupolar component because you are doing such a spectrum. Okay? So you can you can study another one. No. The best is to optimize the velocity. As I mentioned, but they were discussing, they will discuss the movement of the source. And now you can see that you have an asymmetry. So you have to optimize the velocity to record spectrum. Another problem is in the case of ferrite. I did not show this slide this week. So the same experimental spectrum, and you have 4 different fits. Because for you, the main question is, what about the content of iron located in tetrahedral and octahedral sites? So I would take the computer. But the computer is taking care of the minimum of chi-squared. He is not thinking. And finally, I can put some constraint, line width and so on. And you see that the fits are not too bad. Now the question is, which is the best one? So in such a case, oh, sorry. Okay, so yeah, okay. So to continue on the problem of fitting, it is not related to pure Mossbauer spectrometry. So for example, this paper appeared in Science in 70s. So the topic is another one. It's not Mossbauer spectrum. It's between neotropical pollinators in an African honey, bees. So you see it's other topic. The problem was to fit. And the first guy put some Gaussian. 2 weeks after appears another paper in Science with another fit. Okay? Of course, it was a bit of joke. But the idea was to show that in some cases you have plenty of models. So be careful to this. It's not restricted to Mossbauer for any techniques, any result. Okay, so it was his reply. So finally, to treat an experimental spectrum, what you need? You need some theoretical description. Okay? You need to determine what are the physical parameters. Okay? After, what about their physical interpretation? Is there a single solution? We have seen this week sometimes for the fits. Okay, it was one result among
you
lot
have
of
shown
them.
four fits. You have shown 4 fits.
For example,
What they are?
we will see after. And what about the errors? Because sometimes the computer is giving errors, but what are they exactly? So, in the case of Mossbauer spectrum, because first points are not only for Mossbauer spectra. After, you need to estimate the hyperfine parameters. So what we have calculated, we have discussed, hyperfine field, isomer shift, and so on. And also to need some chemical, structural, magnetic information. And of course, on the sample, sometimes it's stored. Because maybe you forgot the sample on your desk, it was very sunny, or the atmosphere is very humid, very wet, and maybe it could change. So you have to take into account on the story of the sample. So in this case, I don't want to put you afraid, but there is plenty of parameters, all were done, and so on. And of course, there is plenty of code. We will discuss, but be careful to this, because you have possibility to put some restraint on. Usually, the student now is taking the computer and is. So no, first you have to think. You have a sextet, you have a doublet, you can estimate by hand, taking some number of square and so on to estimate a priori the hyperfine parameters or approximately, and after to give to the computer. The fit is not perfect, so I put another component. But what could be the meaning to add another component? And so on. So that's very important. And after you have to define a criteria. What about a good fit? You start with key square. But the problem, if you add new components, the key square cannot be strictly compared because the calculation is made here on the number of free components. So you have to be very careful. Probably the best is to look the spectrum and to see, there is a problem, this line is not well described. Maybe there is some shoulder. Where does this shoulder come from? Also. And of course, as I mentioned, sometimes it's not possible, so we change the temperature. Okay?
Greneche, Nishkala wants to ask a question by microphone.
By microphone, yeah. Okay. The lady.
Okay.
Yeah, she would like to make a question.
Okay.
Go ahead.
Nishkala?
Yes?
Eu falou que queria perguntar.
Later?
Yeah.
Okay. Okay, and the last point is this physical meaning. It remains very important. So you have also Monte Carlo, probably they will discuss. You have also some techniques which consist in taking a lot of data and to have some combination. Because, for example, in the case of hematite, you will compare different hematites. But the problem is to know what about the quality of hematite. If it was well crystalline, it was pure, and so on. So to my point of view, while you are considering this method, the result is much more complex to interpret. It's my point of view.
Was it used in mass, this method? The method of the hyperfine data bank?
I think because it was Paola de Souza who made some fit, and he is very fond of this method. The problem also is to know the conclusion, because sometimes there is hematite. Okay, there is hematite with 2.3% of aluminium. Okay? So, typically, be careful to black boxes. They do not think. You are thinking. Okay, error bars. Of course, when you are doing some experiment, there are some errors. Because, of course, you can control by doing some calibration on the velocity of your system, but according to the temperature, according to many parameters, there is small deviations. Okay, we have seen that the source has a line width. If you find something, the line width of which is smaller than the line width of the source, you have to be very critical. So, of course, the statistics is very important. Sometimes it's much more difficult to fit with excellent statistics than a bad statistic. But there is some limits in both directions. So the fit is also hyperfine structure dependent. Depends sometimes on the complexity. We have heard, for example, in the last topic, don't remember her name, on the electron correlated systems, that we had very few resolution, and it's very difficult because there is plenty of parameters how to fit. And of course, what about the validity of the fit? So it is much more user dependent than the computer. And of course, the computer will give you some error. Okay? Isomorphism with plenty of digits. But what is the physical meaning? Because usually you stop at the second digit. Okay? It is exactly the same when people is giving the size of a nanoparticle. So the size with 12.4386 nanometers. What is this physical meaning? It's exactly if I give the distance between Vitoria and Le Mans, plus or minus 3 meters. Exactly the same. So, limit to detect iron. Because sometimes is iron, or as you were mentioning, I have a nice sample. Is it possible to detect some impurity? Here, it corresponds only to theoretical spectrum. Here, I put a single line over a sextet. If I put 2%, you can see the effect. If you put statistics, it will be difficult. The same if someone is writing in a paper, I found this impurity 0.5%. Okay. The opposite is you have a magnetic impurity on a single line. And look, you need 5% to see something. With statistics, that means you need 10%. Okay? Or sometimes what you can do, because of course here you have pure doublet, but if you make a zoom on the baseline, you can see some structure. So you can extend the scale on the baseline. Sometimes you can see something. So I repeat this figure. So if you go down versus temperature, no more changes, except an extension of the hyperfine field. But you will get still the lack of resolution. So what to do is to apply an external magnetic field. We will see here. So you have external magnetic field. You have to know whether it is perpendicular or parallel to the gamma beam. You know it. No polarization effects. So I will explain this. Here you have the scheme of a typical cryomagnetic system. So you have the main coil, which delivers the magnetic field. You put your sample, and you put the source. So the source is there. But of course, the source will be submitted to a leak field, leak magnetic field, if it is too close. If it is very far, there is no leak field, but you will lose photons. So there is to establish a compromise. And the compromise consisted in introducing some compensating coil. This coil will deliver a magnetic field which is exactly opposite to the leak field. By such a way, the source is not polarized. Because polarized means instead to have one line, you will get 6 lines. So in the case of the previous spectra, you had 12 lines because of 2 sextets. So now if you have a 6-line emission, you will get 72 lines. You have 2 choices. Okay. So on the hyperfine field, I did not discuss, but it is composed of a lot of contributions. And one question is, what about the sign of the hyperfine field? Because you have a sextet, you can measure the distance between 2 lines. But you don't know if it is either positive or negative. So that is very important to know if the hyperfine field is parallel or anti-parallel to the magnetic moment. So, of course, if you use external magnetic field, you can obtain such a result. It's not possible to conclude from a sextet it's ferromagnetic. And there is a lot of papers. My sample is ferromagnetic because I have a sextet. No. There is a magnetic order of iron. Ferro, antiferro, it would be the same spectrum. You are not able. But if you apply an external field, you can be able. And there is also the problem of dynamic. So I will not discuss after a few examples the dynamics in the case of nanoparticles, but you have to imagine that sometimes magnetic moments are fluctuating, if you apply an external magnetic field, you will block the magnetic moment, either parallel or anti-parallel, or you will tend to. So now, you have a random powder, you have a sextet, 3, 2, 1, 1, 2, 3. Okay, you have a ferromagnetic powder, so the magnetic moments, the external field. So now you have to know what about the hyperfine field. In such a case, it is opposite to the magnetic moment. And what you will see that you have to subtract the value of the applied field. And finally, in the case of external field parallel to the gamma beam, you will obtain this. That means that with a decrease of the distance between external lines, and you have also a disappearance of such lines, as we discussed before, according to the orientation of magnetic moment respect to the gamma beam. So, by such a way, you can conclude, you have from 301, your hyperfine field is anti-parallel to the magnetic moment. So it's possible to do the same, but it will be larger. It's opposite. Antiferromagnetic powder. So if you have antiferromagnetism, like this, if your magnetic moment is like this, the tendency is to put the magnetic moments perpendicular to the external field. It's the minimum of energy. That means you will get this. For the effective field, you will do the vectorial sum of the hyperfine field plus the external field. Taking into account that the external field is about, I would say, 10 of Tesla, and the hyperfine field is 50 Tesla, you will see that very few change in the external line position. But the main change is here. Before we had disappearance, maintenant we have 3, 4, 1. So if you have 3, 4, 1, you can conclude you have antiferromagnetic coupling. Okay? And in the case of a ferromagnetic powder, so that means you have two types of magnetic moments, usually located in octa and tetra. So I will say before, the hyperfine field is opposite. So the hyperfine field are there for tetra and octa. And if you do the spectrum, as I showed before, there is no resolution. Now you apply an external field. You can obtain the effective fields. And the spectrum you will obtain is like this. By such a way, you can estimate correctly the proportion of tetra and octa. In addition, you can conclude also what about the mean angle between the tetra and octahedral magnetic moments independently. Okay, so I will not discuss on this because it's much more. So, to make a general view, especially for the first column. Okay? So now, we'll not discuss on this. So what I was mentioning before, so we have some clinochlorine sample. We have a nice spectrum. So it's possible to fit. I put one doublet, I put another doublet, and another doublet, and another doublet. And at the end, you have some doublets without physical meaning. So we know that in such clays, you have series of dioctahedral, trioctahedral layers. So we have rotating the sample. You see now an evolution of the doublet. And now you can fit with doublets with the same intensities of line. The reason here was the texture, the preferential orientation. So, okay, it was the case of pyrite, to reply to, I do not remember her name. Yeah, because here you have the red component, no, the blue component, the red component which corresponds to purite, and it is overlap with the other components. So I was speaking about the sensitivity of the technique. Maybe 10 minutes more. I will finish with. So we have a sample, a chemical sample. So this fluoride, and we were rather lucky because the lines were very well defined. So good sample. You can estimate easily isomer shift 0.3 at room temperature, ion 3+. Okay, the chemists were satisfied. So now we have done a series of spectra versus temperature because they were suspecting the presence of a phase transition. And of course, when you look not carefully, you will see that it is for the isomer shift. So the isomer shift is increasing with the when the temperature is decreasing. Okay, right. Here you can see the evolution of the quadrupole splitting. So it's a rather, if we do some zoom, you will see some changes. So we were not sure, so we repeated the experiments. And we were using the cryophones, so we were in the same conditions. And what happened? Finally, we have ion 3+, 3d5. That means if there is a change of quadrupolar splitting, we have a change of the lattice symmetry. So phase transition. Okay. And you can see now, so in this case, you have octahedra are dancing, samba, and now they stop. So that means very, very small changes. And after, there was a change on the position of one ion. And it was possible to detect from Mossbauer such phase transition. That means the technique is highly sensitive. Now, there was some discussion this week. So we have such horn magnet. So you know it very well. So there is plenty of iron sites. How to distinguish? Because now we know how to attribute. But at the beginning, with the first pure neodymium-2 iron 14 boron, it was difficult to identify because all spectra are there versus temperature. So, of course, it took time to fit the spectra and to attribute for each sextet a well-established site. And as I was telling you yesterday, you see that your spectra are much broader. Okay, so that means you are highly sensitive to the symmetry. Now we have such a simple system. It's mesoporous. So if we look carefully, locally we have different units. Octahedral units, tetrahedral units, and pentahedral, hexahedral units. So 6 neighbors, 5 neighbors, and 3 neighbors. Hexahedral is you have a triangle with 2 positions. So 1, 2, 3, 4, 5. Instead of for the octahedral, 1, 2, 3, 4, 5, 6. So we have done some Mossbauer spectrum at room temperature. So we put 1 component, 2 component, 3 component, 4 component, it was okay. And if you look carefully here, the positions of the doublets, you can correlate each doublet to this. Because the isomer shift is sensitive also to the number of neighbors. So the isomer shift of tetra is smaller than the isomer shift of hexa and smaller than the isomer shift of octa. And it was possible to attribute them. And in addition, the quantity of each one was in agreement with the crystallographic prediction. Now, some spectra have been done at low temperature. So you can see change a quadrupolar structure into a magnetic structure. And it was possible to apply the same strategy with 4 components with different isomerships on same quantity. That means at those 2 temperatures, we are perfectly in agreement with the structure, which has been established from X-ray diffraction. So now in this case, you can see upstairs the compositions. Water molecule disappeared from the first one to obtain the second one. So that means it was possible to prepare the 2 samples independently, but the idea was to follow the departure of water versus temperature. So what to do? You have 2 possibilities. You take your sample, you put at 140, for example. And the time to get a spectrum is maybe 20 hours. 20 hours means, is it possible to have a continuous block structure? No. So the idea was using the cryofurnace to put the sample at low temperature, 77 K, to do some spectrum. Then to increase under vacuum, to increase by starting, I think it was 130 for 1 hour and go down to repeat the spectrum. And then 140, 77 K spectrum, and so on, to follow versus temperature by considering the same time at each time. Okay? At each temperature. And finally, it was possible to follow the evolution of the proportion of the first phase and the second phase. Here, to be connected to F factor. The colleagues from chemistry gave me this sample. We have a mixed valence system. X-ray diffraction is 50-50. Okay. By doing the Mossbauer spectrum at room temperature, okay, iron 2, iron 3. But not 50-50. 47-53. Maybe they are about. Wait. What we can do is to do a spectrum at low temperature. Low temperature means 100 because below it was magnetically ordered. But the proportions were the same. That means the F factor was the same for the 2 positions. So because the group, we have done some neutron diffraction, and it is necessary to have a huge quantity of sample, for each batch I made spectra. And the result were systematically 53-47. Consequently, they were thinking that Mossbauer was right, of course. And it was possible to change the composition, which is given here. And after they considered such a composition for X-ray pattern, and it was possible to see an improvement, small improvement of the fit. So it's typical the case where you can improve the composition of the sample. Maybe I will stop after this example. So for these porous systems, the idea is to mix organic chemistry with inorganic chemistry, to take some clusters and to establish some link between clusters thanks to organic molecules through linkers. And the objective is to create some pores. Okay? So the problem is the following. Is the pore empty? Or is it with something? Because of course, by X-ray diffraction, everything is perfect. So we have one sample on the left side. So the student came to me on, I have one structure with a single iron site. Okay, we do some spectrum. But the spectrum consists of two doublets. Two doublets means two different iron sites. Okay, why? I don't know. So I have made complementary measurements to convince her that she was not right. So after a few weeks, she came to me on, by analyzing the Fourier map by X-ray diffraction, maybe there is some water molecules. Okay. And do you have an estimate? More or less, one iron, one water molecule per 7 iron. Okay. Proportions, 85, 15. So rather close to 1/7. So it's finished? No, no. What we will do is to take the cryophones, we put the powder, and we will increase the temperature in order to put out the water molecules. What we have done. And the departure was not completely achieved, but we see that the small doublet is less than the first one. And after what we have done, we open the cryophones, and we put on the table. And one day after, we made another spectrum, and we have seen, I don't know, no, it's not here, the spectrum was rather the same as the first one. That means the system was taking water, was expulsing, and so on. Expulsing according to some treatment. And the other one is this one, another sample. But after treatment, you see that the minor component remains, and the major component disappeared. Situation opposite. So, and after, it was possible to obtain rather the same spectrum. So that means that this one was full of water molecules, since X-ray diffraction was not able to detect. Okay, so probably you are a bit tired or saturated. So I will stop there. So of course, if you have some question, but probably it was quite fast without a question, but more my hands. Maybe they will complete. And to show you from a minimum of examples why it's very important to apply Moss-Bauer spectrometry in complementary to other.
Jean-Marc,
Yeah?
did the water absorption change in any way the recoil free fraction? I mean, did it affect it the
No, because
a factor?
if you want, the idea is the mineral cluster is rather rigid. And after, the water molecule is stick inside the core.
The surface area, on the surface.
On the surface area. The problem, the question is, because when doing some spectra, it is a result, but sometimes when I was receiving some powder, doing the measurement at room atmosphere, as well as room temperature 70, and after using cryophones. First, 70 Celsius. And you can see some changes, probably to some water molecule which were weakly linked to the surface. And at 100, much more, and 120, much more. Of course, if I want to 400, I will destroy totally the structure. But it is very important this, and recently, the chemists were successful in putting some nanoparticles. And the idea was to check what about the interaction between nanoparticles and the matrix. But before, it was necessary to know whether the nanoparticles we were studying, they were inside or outside.
Just a question. If you just take the comparison in areas of the sample that suffered interaction due to the water, the most bounded the surface will be weaker, probably, if I understand well. So a direct comparison of areas will not tell you, like, say, well, I have 60% of an internal phase and 40% of a surface, because the sample at the surface will absorb less.
No, but
so there is a bias, no?
it's a bit related to the question of Kite. So that means you have a rigid mineral cluster.
Yeah.
It is well fixed. They are octahedral units. As they are illustrated, tuck. There. Okay. They are linked together. After, because in such a case, you can see the volume of the pore, the maximum, I think it is about 4 nanometers up to now. So, of course, the system is breathing.
Yep.
You can absorb water molecules. So now the problem is to know what about the chemical link of such water molecules. But you will not affect the, I would say, the position of iron or octahedral units. It's only a change of neighboring. Because if you have some iron and suddenly there is some water molecule there, the environment is modified.
Yeah.
So the QS is modified, as you can see.
So you're considering that even with water around the iron, it's still rigid. The matrix is still rigid.
Yeah.
Just
Yeah.
Small particles that can be detected because of recoilless. No, this is it's something that was. You say that there is a limit in the size of the sample. I was asking myself if you have seen that situation in some experiment, and if it's not true that even if they are too small, as they are as powder, they don't have recoilless because of they interact with the neighbor.
There is a paper, I think it is in 96, it is peer review, and you have spectra. And of course, the quality of spectra is not good. As I mentioned yet, I think it was on Tuesday, so the idea was to insert nanoparticle in a resin. So of course, because they were linked to the resin, after maybe a few hours, the spectrum was nice. But the problem, if you want to study the surface, now there is no surface. So you are totally modifying, finally, the properties of itself, of the nanoparticle. The problem. It depends what is your objective.
Greneche, maybe you can talk about, because this is a very complex question. For example, if you reduce too much the size of the particle, so you have a very big surface contribution, which has different Debye wall effect. That means, so it's not only due to the size, but it's due to the changing the dynamics of the atoms that are in the surface.
Sure.
So, and then you have to go down in temperature to see this kind of difference, and you have to do many things. But this is very complex.
Everybody, well, I am Francisco Sanchez, and we have prepared this. I don't know if I should mention it as a class, but a discussion that we can have together with Gustavo Pasquevich and sorry, yes, from the University of La Plata and CONICET. This is our Institute of Physics. Up there, I'm sorry. This? Ah. Right. Well, in the upper part is our new building, the building we are working since 2018, and at the lower part is the. It was. the historical building of the physics department in La Plata. La Plata is a kind of new city. It was settled down in 1882 to become the capital of the province of Buenos Aires, because Buenos Aires became at that time a federal district in town. The province of then the province of Buenos Aires needed to have a new capital. So it is more or less, it's highly linear, La Plata, contrary to atrás, okay. Contrary to Vitoria, which is highly non-linear town. Well, these are some views of the town. The prefeitura, I mean the municipality, the town hall. This is the cathedral of of La Plata, and some of the places that you can visit if sometime in the future you visit us. Well, and this is the places where there are laboratories of spectroscopy and power, or spectrometry and power, I should say. But there are, I think, maybe 4 laboratories working now. 2 are in the University of La Plata, one in the physics department and another in the Institute of Physics, and then another one in the University of Buenos Aires, another one in the Commission of National Energy, Nuclear Energy. And there is one equipment in the south, here in Bariloche, but it's not being used. Well, this is the laboratory at the Institute of Physics. Gustavo Pasquevich has done a lot of work to get this laboratory working. After we moved to this building, it was a lot of work to do, not only moving the equipment, but also to having the authorization to bring the most power sources to the laboratory and start working again. And also there was a big effort to buy new sources, sometimes with success, sometimes not, because of the sometimes because Russia is the producer of the sources, and some means of financing that do not accept buying from Russia because of the origin of from the Inter-American Bank of Development of the funds, and then because we couldn't transfer the money because the war had already started. And this is a little bit, I'm sorry, this is in Spanish, the facilities that we have at the Institute of Physics. I would say we don't have a very large or impressive equipment, but the laboratories are working very well, are very well interconnected, and we work on the basis of responsibles of laboratories, but not owners, so that these responsibilities may change from time to time. But in principle, we want to have an open policy so that you can perform all the measurements that you need without any problem. Okay, so we will discuss, I think, just about the basic experimental setup because of time. And I think this is enough for today, and maybe a little bit about good experimental procedures and practices. Though Jean-Marc had already told us very important hints on how to deal with most power spectroscopy. I remember when I entered the laboratory to do my PhD thesis, in 1969, a lot of time ago. We only had two hyperfine techniques at the laboratory, perturбable angular correlations, and my power was just starting because Roberto Mercader has make his PhD postdoc position in England with Greneche, and then it was started this technique. And I think this happens all around the world, that and especially in Latin America, that to start doing physics, science, it was very hard to get large equipment. Okay, but as been shown along this conference, mass vapor spectroscopy is sensitive to enormous number of problems and phenomena, which is very good on one side because you can start to do science with mass vapor spectroscopy. And I think that was the idea at that time. You had just the mass vapor spectrometer and X-ray diffraction, okay? And you should do something with that. But it allowed to form the first researches in the area, and maybe first researches in experimental solid-state physics. And also, well, there is also an interlink between solid-state physics and nuclear physics with the mass vapor technique. But it is sensitive, as it was said, concentration gradients in your sample, surface versus bulk, a problem of bounding the way your nuclear probe is bound to the solid, and so it is sensitive to so many problems that of course we have to be very careful on how we interpret the results. And of course we know that now the approach is much more multidisciplinary and multi-technique especially, and so that you can confirm with the several techniques what you are seeing, and more especially your hypothesis, because the hypothesis could be all very good, but you have to prove them.
May I have one question? Two questions. The first one, how old is LACAME University? The second, so you mentioned that you did the PhD. Have you done it in our university or not?
Yes.
Oh yeah, in 65. That means
69.
69,
Yeah.
That means that you had PhD from that time.
Yes.
And how old?
Well, it was the
That's an important
what?
in South America, because, for example, we had a PhD at Memphis in 1993. So in 2003, 1993 we got a master condition, but only 2003 we got this.
Well,
To have a PhD.
there were some up and downs, of course. The university is very old for us, of course. It was settled down in 1989 as a provincial university, and in 1905 became a national university. And then the physics department was founded in 1905, or maybe 3 years later, 1908 or so. And a German professor was brought to lead the physics department, and he started directly with experimental work. That was very good, but then things happened. I mean, that sometimes the things were better, than sometimes they were worse. So there was times of flourish, of getting better, as sometimes it was. But I think the PhD was much before I did mine. There's a book with the records of PhD works at the uni.
That means I think it's probably the first company in South America that had the PhD. In
Maybe, but I don't know. I don't have the answer to that. Okay. Well, as you know, this is a resonant process. So we need a source which emits photons with exactly the energy that you need to excite your nuclear probes that are in your sample. Your sample, of course, you can make it with just pure iron, because pure iron has about 2% of iron 57, this isotope, which is the one on which we can perform the most power spectrum. So there are other ways, of course. It could be the reverse. If you had cobalt 57, for instance, a liquid or something, in any chemical form, then you could manage in a hot chemistry way to put this cobalt 57 into your sample and then you need to have a very good absorber, as an iron foil, probably made of steel or something with just a single line, as thin as possible, but made exclusively of iron 57. Then in such a way you could perform a different mode of a spectrum, a spectrum which we will call of emission spectrum, because your sample will be radioactive and your absorber will be not radioactive. But what is normally happens, I'm sorry, is that you have a source, a commercial source that you buy here with a red star, and you need a motor to move the source up and down and give to the gamma rays an additional Doppler energy, so you can record absorption as a function of energy of the gamma rays. And then you have your absorber, of course, here, and a detector of gamma rays. And then this is an absorption spectrum. What you see is what you don't get. I mean, it's the gamma rays that were absorbed at that particular energies. You have less counts, okay? There are other possibilities, but this is the most usual one. And then, of course, you have to polarize your detector, usually to 2000 kilovolts or something like that. And then you need also to set of processing of rapid signals, electric signals, which begins with a preamplifier here, an amplifier, and I must say that source does not emit only the most power radiation of 14.4 keV, but there are also emissions of X-rays and other radiations of higher energy also. So you need something to select the rays with the right energy. We usually do it with the help of an oscilloscope. And then you have the counts that in principle belong just to the most power radiation. On the other hand, you need to move your motor following certain protocol. So you have here a signal generator. It is the most common way to do it is with a triangular wave. This triangular wave enters in this servo amplifier, and this sends the signal for the motor to move. And of course, what you need also to check how out that the motion of the motor is as you expected, or at least that there are no extremely important deviations, and also to be sure that if there are deviations, they are not in the range of velocities on which you are going to record your spectra. And then this signal generator habilitates an storage device where you are going to record in different channels the information that comes from different velocities, which means different energies. Well, this is an old traditional setup. I mean, I have put here the real moduli that are used in the laboratory instead of the previous scheme. Now there are also much more a tendency to have integrated systems. If you buy a system from Bissell, for example, it will be much more integrated than this system that is composed of several separated moduli.
What would it be the most power drive here?
¿Cómo?
Can you come back to slide?
Sí.
The most power drive. Oh, what is it?
Ah, you mean this is exactly it's an amplifier that amplifies your signal generator signal adequately, so you can move the driver. It needs some voltage input. I mean, the amplitude of the signal that you send there has to be in certain range, and then there is also I'm sorry, I think I made a mistake, but I don't know how to go back. To the presentation. But from the motor you can take a signal that follows the real motion of your motor, and then you compare this signal with the signal you sent to the motor, and you see what are the differences. This is called the error signal, and then you try to minimize this error signal in order to have the best motion of your motor. Well, these are some prices. I don't know if they are actualized or not. At the time I started, an spectrometer was bought by less than $1,000, and we had just a spectrometer, room temperature, and no additional equipment. Okay, but if you want to add at least a cryogenic system, then you need a lot of more money, and the sources are expensive too, and maybe they will be more expensive in the near future. I don't know. Now we cannot buy sources because the only producer is in Russia. It's impossible. But if sources are going to be produced in other countries, for instance in the USA, I don't know if the prices will be the same or not. Well, the question is that this is a very important part of the equipment, because it's where physical things happen. Okay, where the absorption takes place, and then we have to have very careful in concerning the alignment and the distance between the source and your sample. Brilliant. Okay, we are going to talk about this a little bit more in a few minutes. And I started now to mention some characteristics of the radioactive source. That the radioactive source for iron-57 spectrometry is a source of cobalt-57, which is dispersed in a matrix, usually rhodium. Rhodium is used because it is very rigid, so that the binding of the your nuclear probe to the lattice is very good, and you can have decent, very decent Moss-Bauer record fractions. And but this, as we will see, also it is used because it has no internal intrinsic magnetic field. It's not a magnetic material, so that you don't expect to have a splitting of the lines that are emitting because of a magnetic field. And it has a cubic structure. So if you have rhodium, which is very pure, and you have your Moss-Bauer probe substitutionally in that lattice, then there will be no electric field gradient, and you will not have a quadruple splitting. But of course, your probes. I'm sorry. But of course, your probes are must be sufficiently separated from each other so that there are no interactions between the cobalt-57 impurities. Otherwise, they will produce some sort of interaction, hyperfine interaction, that it will be present in your spectra. Okay? Of course, so the diffusion of the cobalt-57 into the rhodium matrix must be made very carefully, so that if there are some interactions, they are very minor and statistically will not affect your spectra. Well, this is a typical Moss-Bauer source. It's a very thin layer of rhodium with a cobalt-57 in it, usually covered with some kind of protection which should not absorb sensibly the radiation. So it could be kapton, it could be aluminum also, it could be, it might be very thin, and or sometimes beryllium. Beryllium is very much used, and kapton, okay? Well, and we must be very careful when we handle the Moss-Bauer source, because the Moss-Bauer source, when you buy it, is 50 millicuries, so it has a lot of radioactivity, and then you have to have in your lab the tools and procedures that are adequate for the manipulation of the source. And of course, you have to be do this as fast as possible anyway. And that's also a reason for, I think, that the Moss-Bauer laboratory is usually during the day empty. Nobody's there. You only go there when you need to go, but you stay there just the amount of time you need to be there. Okay? That's why what Gustavo mentioned during his talk of this system to change remotely the samples that you are going to measure is a very good idea. Of course, it cannot be done in any physical situation. If you want to measure at low temperature, then you have to go there and replace manually the sample in your cryogenic system. Okay. And sometimes you see that there is a little border here. This is in order to focus the beam of gamma rays, and so that depending on the angle respect to this axis, you will have more or less radiation in the lab. Anyway, all these systems are well, are surrounded by some absorbent material, like lead, for instance, in order to avoid that the radiation spreads everywhere. Well, here there are some types of sources with aluminum window, with kapton window, for instance, and if they are appropriate for certain conditions of operation. Okay, I'm going to And as I say, well, we try to buy sources of 50 millicurie because it's useful for us. It gives us some time, enough time between the need to replace the source. But as you see, if the activity of the source increases, the line width increases too, because then you need to have more cobalt 57 in the rhodium matrix, and the probability of interactions between the cobalt emitters increases. Okay. And usually, what you see if you obtain a gamma ray spectrum from your source, then you see several lines, but you're interested in this line. This line is the one originated in the photons of 14.4 kV. So you have to have a mean to get rid of the gamma rays which don't belong to this particular line. Well, I think this is I don't know why is this slide here, but of course Jean-Marc already talked about this. Well, the motor is usually has coils inside with a magnetic core, so that you can have on one side a driving coil which brings the signal from your signal generator, and you have a sensor coil, so you can monitor how your motor is moving. Okay. And in one of the extremes of this axis, you have your radioactive source. Well, this is a typical motor from Bissell, and this is more or less what you see. You have here, this is your velocity wave, and this is the error signal, which is the difference between the signal that you, the response of your motor and the signal you have sent to the motor. Then you need to minimize this signal as much as possible. And you see that it is almost impossible to make it zero, where the acceleration changes up suddenly of sign. This, as you see, this is a triangular velocity wave. This means that this acceleration is constant in each of these parts. Okay? It's constant and positive here, constant and negative here, constant and positive here, and so on. Okay, so here there is a very large acceleration, because you have to change from a positive acceleration to a negative acceleration, and then it's almost impossible to control the motion of the motor precisely in that region. But usually we don't record any information in that part of the velocity range. Well, this is well, any counter, any detector which is sensitive to gamma rays in the range of 14.4 kV, in principle will be useful. Of course, it's a matter of sensitivity, of efficiency of the detector. You need a detector that has to be very efficient at that particular energy range. Proportional counters are very much spread and used, and simply the gamma rays go inside through this beryllium window normally, and then because you polarize with this with a very thin wire in the middle, in the axis of the detector, which is at a high positive voltage, in order to attract the electrons that are produced when the gamma rays enter the detector and ionize the gas inside the detector. Usually this gas is a noble gas with some sort of what we call quenching gas. Because you may produce landscapes, I don't know, avalancha, como dices? Avalanche, okay, of electrons, and maybe this avalanche of electrons are not, I mean, they will block the functioning of the detector. Okay, and well, of course you need a high voltage source to polarize this wire, as I mentioned before. And then it begins the process of formatting and selecting the pulses in. Yes? You can say that it's necessary for the detector to put within LED. Yes. Of course. As Jean-Marc said, you have a case to put the detector inside with just an opening for the window of beryllium, so that there is no possibility that the gamma rays enter the detector anywhere, just where they have to get into the position. But then you have pulses. Pulses are unformatted initially, are difficult to process. So you need to a way to make your pulses nice, and then to amplify them, and then to select only the pulses that you want. Once the pulses have passed through the amplifier is also for some unit that format the pulses. So it makes very nice pulses with the shapes here. And then you can see here that this intense line here, this belongs to this 14.4 kV transition. So what you need to do is to get rid of this and to get rid of what is above the 14 kV pulse. Usually you do that with a single channel selector. It's a device that allows you to put thresholds above and below, and to avoid that pulses which are above or below that thresholds are processed. Okay, and then you, at the time, you remain only with the 14.4 kV pulses. Well, I will skip this one. Well, I mentioned that it's very common to use a triangular wave, but you can use also a sine form wave. Several labs use this, especially in certain conditions where you don't want to have these strong changes of acceleration. For instance, if your source is at the end of a very long road, I mean, because you put your source in a cryogenic system, so that the motor, instead of the source of being stuck just at the end of the axis of the motor, you have there a long road to put the source into low temperature in a cryogenic system. Then it's a system much more likely to have vibrations because of the geometry. Okay, and then if you use a triangular wave, then these problems of sudden changes of velocity might be more important. If you use just this type of wave, the acceleration changes in a much more smooth way. But of course you have this, which is a constant velocity generator. You have also this velocity here and this velocity here, and this sudden change that almost occupies a very few channels of your resistor system. And well, of course, they have improved many different types of velocity waves. What you do with a certain point is to send to different channels the information that corresponds to different velocities, so that you can build your spectrum. Okay? And then what you get is a double Mohbauer spectrum, because you have the part where the velocity increases with positive acceleration and the part where the velocity decreases with negative acceleration. But then you can fold this spectrum. You have to be very careful what is the folding channel that you are going to use, and to get just a single spectrum. And it's not very clearly seen here, but because of this motion of the source, there are part of the cycle of motion where the source is closer to the detector, very little, of course, and parts where it is farther away from the detector. So you end having something like a background, which is sort of increases here and decreases here. You understand? The folding procedure is a way to get rid of this effect, at least to the first order. Okay, these are just... then there is a problem of calibration, okay? And then the most common way to calibrate, there are other ways to calibrate, but this is just to measure a thin foil of iron, alpha iron, BCC iron, a pure BCC alpha iron foil, okay? And this material has been so well studied so far that the hyperfine parameters of the spectrum of the alpha iron thin foil are very well known. So if you know exactly that the position of your absorption lines, then you can calibrate your your velocity scale, okay, and pass from this channel scale to a velocity scale here. This is done, of course, with a fitting program, but in principle, you could do it manually. And many times when you have a Mossbauer course longer in duration, where we could do that with the students, so that you could personally in your desk make a calibration. Well, and this is the issue of security, safety, so that you need to have some tools in your laboratory, like radiation counters and dosimeters, this type of, what is the name of it? It's, no, what is the name in English of this? I mean, well, as a protection. So, yeah, something that you put is very heavy, and before exposing yourself to the radiation, okay? Well, now not all the radiation that goes through the sample is resonant radiation. Not all of it will produce a Mossbauer transition. In part because of this probability imposed by the Lamb-Mossbauer factor, okay? But also because some of the radiation has suffered scattering somewhere, so it doesn't have exactly the energy that you need to produce a transition. So that in principle, you see, you expect to have with the iron 57 ratio of the depth of your lines to the background that you have, usually no more than 10%, okay? Uh, if you have much more than that also, it would mean that you prepare do not prepare very well your samples, because if you put too much material in the way of the gamma ray, you will have absorption effects that will distort your spectrum. Well, and regarding the absorber, it could be of very different natures. You can work with a powder, with a foil, with ribbons. Remember, Edson, when we did this? And sometimes you can precisely choose what will be the thickness of your absorber, and sometimes you cannot, because the sample is what it is, okay? And you must measure the sample as it is, but then you have more work to do to interpret your spectra and to analyze it. And well, this is a typical sample holder. It's made of two small cups of a plastic material. Very good for powders, for instance, and then, well, in our case, this is more or less the size of our sample holders, and you have to be very careful, as I think that Jean-Marc mentioned it today, to make a uniform absorber, as much uniform as possible, okay? So that what you get for any part of your absorber, it's bringing to you the same information, okay? Once I visited the laboratory of C.L. Chin in the University of Baltimore, and the first thing he told me is holes kill your spectrum. And this is very true, because if you have holes in your absorber, then gamma rays will pass freely and contribute very much to the background. And the more background you have, the more Poisson distribution you have also. So that the ratio signal to noise deteriorates. So the absorber should look as much uniform as possible. And then, well, there is a parameter, a quantity, which has been defined as effective thickness of your absorber, to which we have to put attention in order not to have distortion effects on your spectra. So that the effective thickness should be below 1. In principle, at least 1 order of magnitude below 1, in order not to have these effects. Rarely this condition is satisfied, I must say it. But it is very good to keep it as low as possible, okay? It is calculated as a series of quantities which I'm not going to go in detail, but have to do with the amount of nuclei you have in your sample, the cross section for the Mossbauer transition, and so on. But one of the things that happens is that you increase the amount of iron in your sample. This is here as milligrams of iron per square centimeter. Then you see the effective thickness increases very much, but it depends, of course, if you have a singlet or a sextet, because in a sextet the signal is much more distributed, and then this effect is a little bit less restrictive. And in the case of a sextet, it depends on which kind of line we are looking at, because usually the line 1 and 6 are more, in the case of a sextet, I mean magnetically splitted, are the most intense ones. If you don't have polarization in your sample, then these lines are more sensitive to this effect. And then say that you have a random distribution of magnetic hyperfine orientations in your sample, then you expect this ratio 3, 2, 1, 1, 2, 3. Okay, but it will depart from from that distribution to something like 1, something less than 2, and something even less than 3. Okay, because that are the lines which are most intense. And there are some expressions that are used to estimate the line width that you expect to have in your spectrum, depending on the size of your effective thickness, that can be used in different regions. So sometimes, as Jean-Marc said, you cannot have lines which are narrower than the natural width. I mean, but you will have certainly lines that are wider than this value. And this is the natural width is more or less, I mean, the full width at half depth will be is about 0.19 millimeters per second for iron 57. Well, also this has to do with this has done by Gustavo. Gustavo, you want to talk about this? You did it.
This is a simulation where we have where it is discussed exactly what the last slide was showing, that thickness effects affects the line width. So in the center, abajo. 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 Thank you. So in this one, there is a normalization on the depth, and you can see that when you increase the effective thickness, the width starts to increase. In this one, there is the not only increase the width, but also increase the depth. That is quite obvious because you put more sample and you have more absorption. So your line that should be Lorentzian or is for an only absorption atom should be Lorentzian, it start to be not more a Lorentzian line, because the height and the gamma are doesn't increase in the same way. So you have an increase in the gamma, an increase in the height, that in fact it start to saturate. That is the way they are also called saturation effects. It's quite obvious. Like if you increase too much your absorber, you can't absorb more than the 100%. So you must keep a saturation in some moment. You start to increase linearly the absorption, and you start to have a saturation. And here there is the calculation of the different full width half maximums of this spectra, of these lines in the cross one, and the fit of first order and second order that allows you to have a relation between effective thickness and gamma. So from your gamma you can estimate the thickness of, or if you calculate your thickness with the number of atoms and the formulas that put Kike just in the slide before this, you can estimate the gamma. But I want to show the difference with it here in points. There are the half width if you fit your line with a Lorentzian line. So there is different. There is a small difference also between the gamma that you obtain from the fit than the full line width. So there are some, I don't know if next I can also talk about this one. Here you have a doublet, but not necessarily a doublet, two lines. One has the double of absorption than the first one, or than the other one. So in the low effective thickness, where you don't have saturation effects, you measure, or you will see a double absorption relative to the first line. But if you have a thickness absorber with much more sample, just because you make a thick absorber, or because your sample has that absorber and it's your case, maybe you will read something different. So if you here your result says that you have the double of sample of iron in this line than in this line. If you don't care about effective thickness, you maybe can say that you have almost the same in both lines. So it's there to take into account.
Okay, thanks, Gustavo. And let's see. Yeah. Well, this is in many experiments it can be seen very clearly, this effect of the thickness of the absorber. I would say that if your absorber was very thick, even you can have a flat bottom of your lines, something like this, okay? Completely distorted from the Lorentzian way. But here, for instance, this is a material, iron tin 2, which is heated up and measured inside of an oven. And you see at room temperature, quite well, the sextet. This is an antiferromagnet seen from the iron side. This can be studied also with tin. It's very nice because you can study with mass over spectrometry, both from the iron side and from the tin side, okay? But at a certain point, this antiferromagnet at the nil temperature, it becomes a paramagnet. And all the observation that you have spread in a larger range of velocities becomes concentrated in just one line. It means that from the point of view of the thickness of your absorber, now your absorber is thicker because all the probes absorb at the same energy, at the same velocity, okay? And you see the spectral area is decreasing, not only because of this effect, but also because of the Lamb-Mossbauer factor. But here, where the transition takes place, there is a sudden reduction of the spectral area, okay? Well, sometimes you need to make a dispersion. You have very little absorber, or your absorber, well, for some reason you need to disperse the absorber in an inert substance, which must be inert from the point of view that it doesn't interact with your sample, chemically, for instance, or magnetically, or whatever, okay? But also from the point of view of having very low absorption of radiation, it must be done with a species of very low C as possible, atomic number, I mean. And then you make a dispersion of your sample into this material. And again, you need to have a very good dispersion, very homogeneous dispersion. Not something like this, but rather something like this, okay? Okay, and then we have also cosine smearing effect that we must take care of, and this means that we have to keep the distance uh, source absorber, or at least the distance between the source and whatever determines the solid angle that the radiation goes before entering into the detector, sufficiently large so that this angle is not too big. Because if this angle is big, it will happen that at the different positions of your source, you will have different dispersions of velocity. And only the gamma rays which are emitted along the axis between the source and the detector will have the right Doppler energy, because otherwise the component of the velocity in the direction of the gamma ray will be smaller, and then these photons will carry less energy than the photons which are emitted along the axis, okay? And then this will produce a smearing out of your lines. And this has been studied. Let me see. This is one of the first works where this problem was treated and demonstrated the effect that it produces. This is, for instance, this is an old paper. You see the few points describing each of the lines of the morphological spectra, but it's what people could do at the time. And you see, this called this high collimation, which means that the distance between the source and the collimator is long enough according to their standards, of course. But if you reduce that distance sensibly, you see that not only this line begins to be wider than the others and is wider than this, but also the height of the profundity, the depth of the line is smaller than it should be. So if you are not aware of this, you may think that there are some sort of polarization effects or something like that, which is not the case. So what I am focusing here, and I think I need to finish now because of the time, is some certain cases that you have to have when you record Moss-Bauer spectra. There are some other situations or that you must have in order to analyze and observe your Moss-Bauer spectra. I think I'm not going to enter into that. Let me see. No, I think let me go to the end of the talk. I am not going to talk about the additional experiments, but I want to see if we have something important to mention by the end of the talk. And otherwise, well, of course, there is the issue of the fitting program. Okay, so you must know what fitting program to use. I recommend that you talk to your advisor or someone that you know that do good Moss-Bauer spectroscopy and ask their opinion to see with which program you should start to work with, and to have some tutorials also about how to use the fitting programs and take into account the hints that Jean-Marc mentioned before. But in the web there are available Moss-Bauer programs to do the fitting. But before starting, it's better to get aware of it. And well, first of all, as Jean-Marc mentioned, in principle the transitions have Lorentzian shape. Then because of the way your sample was constructed, or the way your probes are distributed in the sample, the way the hyperfine interactions are distributed because of this or any other reason, the lines of your spectrum may not be Lorentzian. But you can always, in principle, unless you have dynamic effects, I mean, if you have a static spectra, you in principle can build your absorption lines as a sum of Lorentzian lines, okay, with a physical criterion. You can do that. So remember that because this is important. Well, I mean that the properties of the solid, electric or magnetic, can be distributed for compositional reasons, for structural disorder, for chemical disorder, for occupation of substitutional or interstitial sites of your probe in the material. Then you have to use some sort of distribution function in order not to have to use so many subspectra. Okay, you can make an histogram, and that's okay. Each histogram only for a signal with the Lorentzian shape and more or less the natural width of almost 0.20, 0.22, a little bit more than natural width. But also you can, based on a physical approach, decide if this distribution of properties will be a Gaussian distribution, a log normal distribution, or what, and then to create a more friendly fitting procedure which does not need so many parameters to be fitted. Remember that if there are no asymmetry and anisotropy in the elastic properties of your material, and you don't have also texture in your sample, your doublets always have to have the same profundity, the same depth. Remember also that for causes of polarization, magnetic polarization of your sample, you can go from intensities from 341 to 301, okay? But it never can happen that you don't have lines 3 and 4 in your spectra, for instance. So, because sometimes the Mobile program, it may let you do that, okay? If it doesn't have the right constraints, you may end doing a physical fitting. Sí.
It may be important to say that when you, because in some cases it's possible to measure spectra from single crystals. When you measure single crystals, the range of the densities, it depends on the geometry of the hyperfine interaction. So this ratio 3 to 1 usually applies to powder samples.
Certainly. If you measure a single crystal, then probably the hyperfine field will have only certain allowed directions. If it is a cubic system, maybe 3 directions which are equally alike, but you would not have a random direction of the properties in your sample, and then you must take care of this. It also imposes certain limitations on the thickness of your sample. Sometimes you cannot make the sample as thin as you would like to do it, or your sample would be very small, and then you have to manage to measure such a small sample. Well, a lot of situations appear in the experimental work which are not possible to anticipate in a short discussion, but the important is to know the basic things And of course, there are materials like amorphous materials, especially magnetic amorphous materials, where the spread of the signal is exceptionally large, okay? And then you need many, many subspectra in order to give account of your spectrum. And this can be done, as in this case, putting many subspectra with some restrictions, or you can also use a distribution of hyperfine fields, just a function with a distribution of hyperfine fields, which usually needs to take into account certain correlations between the distribution of hyperfine fields and the distribution of isomer shifts, okay? And also correlation with the quadruple interaction. But this is a little bit more complicated, because imagine that you have a pure material, for instance, a cubic material, which has your probe in one substitution in one point. Then you wouldn't have any electric field gradient around the probe, because it's surrounded in a cubic geometry by atoms all of the same species. Now, if you put one neighbor of the same species as your Morbauer probe, then you will have a quadruple probe splitting because of the electric field gradient that is created. Probably if you put two, you would increase your electric field gradient. But after you fill half of the first coordination sphere, then the electric field gradient will begin to reduce. If finally you have 8 near neighbors, for instance, in a cubic centers system, then your electric field gradient will be 0 again. Okay, so the correlation between hyperfine field and quadruple interaction, in principle, should not be linear. Okay, unless you are working at a range of concentrations where you can disregard these extreme situations that I mentioned before. Okay, so well, it was a pleasure to be here with you for the conference and also for this class. If you have any question, please ask. Otherwise, I think it's time for lunch. Yes, Jean-Marc.
Probably a question to go in your sense, because, for example, here there is 8 components. So the idea is not to attribute to each component some physical.
It's not to attribute to each component some physical site. Finally, the main important parameter correspond to the mean values of the component, of the each parameter. And what you can do is, because as Kike mentioned, so we can put 8, maybe 10, maybe 20 components. But if you look to the mean values, they are quite constant. And it's only this way to have some physical meaning. Because sometimes there is some people, they are introducing 45 components. What does that mean? No, but it's true. So recently I have seen a paper. There is the figure is twice higher because there is all components. But what is this? In addition, the hyperfine parameters were given, and there is no strict correlation. Because sometimes you can see a value of quadruple shift. It's very high. And no comment. So, but only the mean values, the mean hyperfine field values, the mean isomer shift, including if you are using some correlation. So it is a proof of the truth of the parameters. But to discuss the 7th component,
then you may end following the statistical dispersion of your spectrum.
Yeah.
Because the fit will try to be the best possible one, and then you will have a theoretical line that follows your statistical deviation.
And in addition, because you gave the list of softwares, so MOSFET is not. But once in the lab, there was some colleague as postdoc, and he showed me some result, and I was not convinced by the result. So I used another software, and finally I have seen that there was a problem in one assumption in this case. But once we have considered the same assumption, the resulting data were exactly the same, including the 4 or 5 digits, because each of parameters are using the same diagonalization matrix. So the mathematics are the same. It's only in one case the line will be blue and the other one will be red, and so on. So it seems that it is not dependent on the software. It's much more dependent of the assumption you give to the software. On the operator, of course. On the last point, I want to say that each sample is at each time a new story.
Another thing maybe is to have as many information as possible, because with that way you can build a proper physical model to interpret the Mossbauer spectrum. So some time ago I have seen people that get the spectrum and try to fit anything with no idea what they are going to extract. So it is important that you combine all the measurements, that you have all the characterizations and build a physical model to try to get the correct interpretation of the data.
Now I have to bring my experience with another technique. You have to be careful with bias, your bias, because you may believe that that sample has that component. You want to prove that that sample has that component. If you do not prove, you lost your time in the lab, you know. So you will put the Lorentzian there, doesn't matter what. So be careful with yourself.
So just to make sure that I do understand what you're talking about, when you say constraints, is like an initial guess for the coefficients, or? Okay. 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 Oh, I get it.
La próxima.
I used 2 tricks. First, the last liberty that I gave the better.
No, the last one.
Last,
This one.
Next one.
The next one.
Next.
Yes. At the top there is
Oh,
the
okay.
correlation between the isomer shift and the hypergram field. Correlation between the quadrupolar and the hyperfield.
Okay.
Linear correlation.
So, you guys get this from experience or literature? It's a
This is
mixture.
going to reduce the free.
Oh, okay.
But can we this shape of the spectrum?
Yeah, that's.
But the idea is asymmetry.
Yes, yes.
The idea is behind this situation where you have a distribution of hypergram fields, we assume that they can because your thank you. It's in different environments. That's the reason because you have different hypergram. So if you change from one hypergram field to another one, you can think that your isomer shift is changed in
Okay.
The surround doesn't change too much.
Yeah.
And then you have to have a small correlation because the line, some of the line are so overlapped.
Okay.
So to take this asymmetry, because you have isomer shift and also the magnetic hyperparameter, that's the split.
But
So you
this
take
is
this.
also always based on a physical model. It must be based on, okay, if you put, change one atom of the material next to the probe with a different one, with a different electronic density, then you would expect to have a change in the isomer shifts here. And if it does affect at the same time the magnetic properties and the magnetic hyperfine, you may assume that there is a correlation between the two parameters, and the simplest assumption is that this correlation is linear.
Okay.
But this is a sequence of
Triangle.
assumptions,
Yeah.
which must to be very well physically supported.
Okay, thanks. On this case, for example, if you assume that you have a distribution of metaphanic field, for 20 values, you have to consider maybe 20 values of isomer shift. 20 plus 20, it's much more. No, but it's much more than the number of experimental points. So you have to reduce. And of course, the linear correlation is not physically, as you mentioned, it's not physically elegant, but it is not too bad.
It's like solving a single equation with two unknowns.
Yeah. That's it.
Okay, back to the models and other works. And anyway,
Oh.
the less degrees of freedom you have,
Yeah.
always,
Mm.
because you put, as general rule, at least that's why I use, the less components that I can fit in the spectrum, the better.
Yeah.
You know?
So
Because
It must be a rule.
yeah.
yeah.
So once again, Kiki, Jean-Marc, Gustavo, thank you very much to all of you to stay here during this Friday afternoon. We stay from 9 to almost 1 o'clock. We thank very much the student and all of you that has been with us. I would like to make some special thanks to Zé Rafael that stay with me during most of the last 6 months. And I'm sure that this time for you that are finishing your physics course, you may decide which area you may go. So that would be a very nice opportunity to see that we have much more than gravitation and field theory and other things. So in physics, for example, we have one technique that's very powerful. It then can be used in several areas. So in chemistry, in biology, in physics, in metallurgy, engineering. So you may have some new opportunity to choose your new career. You know, that's the main point. And in general, I would like to say once again, thank you, Kiki, thank you, Greneche, and thank you, Gustavo.
Thank you, you all, Edson, for this conference and for the warm treatment that you have given us, not only here in this room, but also in the lunch and wherever. So we have passed a very, very great time here in Vitoria, thanks to you. Thank you.
Okay. We thank to all of you. Now it's closed. So LACAME has finished. We have to wait for 2 years. It will be in Cusco. Probably some of you, you'll be there.